Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is how to perform power factor testing with Megger Delta 4000 instrument. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. Oh, Charles, I think we might have our slideshow still paused for our
Oh,
introduction. There we
uh,
go.
okay. Sorry.
No worries. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Dr. Charles Nybeck, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Dinesh Chajer, Technical Support Group Manager, and Daniel Carreño, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Charles.
Thank you, Michael, and thanks everybody for joining. My name is Charles Nybeck, and as Michael said, I'm an applications engineer here at Megger, and today we'll be discussing how to perform power factor testing with Megger Delta 4000. Looking at today's agenda, we'll start with a brief introduction of what is power factor. Then we'll move into why perform power factor measurements. Then we'll talk about the power factor test modes, then move into factors affecting power factor measurements. And then we'll go right into the Delta, covering the hardware overview, followed by the software overview, and then wrap things up with a discussion covering advanced transformer insulation diagnostics. Let's get started with what is power factor. Now, when we talk about an ideal insulation system, we have in the diagram here a conductor for our high side and a conductor for our low side, separated by the insulation, bulk insulation in between. And we could look at that as 2 conductors separated by a dielectric. And we all know that that's the same as a capacitor. And for an ideal system, when AC voltage source is applied, the current is 100% capacitive and leads the voltage by 90 degrees, as seen here. And this is important to remember because for power factor testing, you apply an AC voltage and then you essentially measure the leakage or loss current through the insulation. So in this case, in the ideal case, there would be no loss current because all of the current is 100% capacitive and would be 90 degrees. And we'll look at why 90 degrees would equal 0 as far as power factor. Now, we all know that in practice, no insulation is perfect, and therefore there's always going to be some amount of loss or leakage current that's in phase with the voltage as seen here in this diagram. Now, so not only will we have a component of loss or resistive current, but we'll also have our capacitive current that's still 90 degrees out of phase. And what will result is this diagram to the right, where we have a total current that's somewhere in between 0 and 90 degrees, resulting in this theta angle here, and a delta angle that's, the theta is your angle between your resistive current and your total current, where your delta is between your total current and your capacitive current. And that's important because the cosine of the theta or power factor angle is your power factor, which is the relation of your resistive current to your total current. And another popular term is tan delta, or dissipation factor, in which you look at the delta angle that is between your total current and capacitive current and take the tangent of that, which gives you the relation of your resistive current and capacitive current. And in this case, we can see that the theta angle is less than 90 degrees, which will result in a cosine of theta that will be greater than 0, since cosine is less than 90 degrees. And we know that cosine of 90 degrees is 0, which is why the ideal case was 0 as well. Now, what this does is this essentially sets up a model for power factor transformer testing, in which, and we'll discuss why these are shorted a little later, but we have a conductor that is our high side, our conductor on our low side, and our ground. And looking at that, we know that we have insulation between each. We have insulation between our high and low, insulation between our high and ground, an insulation between our low and ground, resulting in these 3-capacitor network as seen over here, where the capacitors are represent the insulation between each of your nodes or each of your electrodes. So your CHL would be the high to low capacitance, or rather the high to low insulation, and your CHG would represent your high to ground insulation, while your CLG would represent your low to ground insulation. So now that we've briefly discovered what is power factor, let's talk about why we perform the measurement. Let's start by taking a look at the typical transformer life cycle. Here in the x-axis we have the transformer's age, and in the y-axis we have the stress and withstand level, where the black line at the top is the design withstand to begin with. We can see the stress kind of in this gray, and the actual withstand in blue, and we can see some normal deterioration just by normal aging, and then we see this abrupt dip here, and this is due to the incident here seen in green, and this could be a fault, or in the case of this incident, could be a defect in the term of an undetected gasket leakage. We see another abrupt drop in our withstand, and this undetected gasket leakage is going to introduce moisture and air into the insulation, and now we can see a more abrupt decay in our withstand as life goes on. And there's 3 cases that can happen here. One, you can get pretty lucky and you have normal life, or what could happen is if an incident happens towards the end of life, you'll have an abrupt failure. You can see that the withstand is lowering. We have this incident, could be a fault or something, and now all of a sudden we've caused a failure within our transformer. And the other case is that you could have premature end of life due to this undetected gasket leakage getting worse, introducing more moisture and air. The insulation is deteriorating because of that, and you can see just a severe decay in the withstand until it meets the stress level and we have a premature end of life. Now, what could happen is you could introduce testing and diagnostics, and this would allow you to make decisions according to factory repair or field action, and cause to increase back your withstand and maintain that over its life and extend the lifetime of the transformer, which is obviously our ultimate goal. I mean, they're very expensive, and we obviously don't want them. We want to get the most out of them we can. And another reason to test power factor is there are international standards, several of them, that also promote power factor testing. For instance, we have the NETA ATS standard here that recommends to perform power factor insulation, or perform an insulation power factor or dissipation factor tests on all windings in accordance to the test equipment manufacturer's published data. Now, we also have the IEEE C57152, that is the guide for diagnostic field testing of fluid transformers. And in section 8, it provides a diagnostic chart listing different test and diagnostic techniques for each component of a transformer. And looking at the chart here, we can see that we have windings and bushings, and for both of those, we can quickly find power factor and dissipation factor tests within the chart, and followed by several other recommended tests as well. So that gives us the why we're doing the testing. Now let's go ahead and we'll take a look at the different power factor test modes. There are 3 test modes in total: the ungrounded specimen test, the grounded specimen test, and the grounded specimen test with guard connection. And we'll go through each one of them briefly and just kind of discuss them. Here we can see we have our sinusoidal or AC source, and we're injecting into the high side. And we can see we can actually sectionalize and isolate the insulation system using these different test modes, because we can see the grounded connection here in green, and we bypass the ammeter here. So we can see that the only tested insulation system here is your high to low insulation as measured by the red lead. If we look at the grounded specimen test, we can see that now the ammeter is going to include measurements from both the ground and the red measurement lead, which is going to include both the measurements including your high to low insulation and your high to ground insulation at this point. Then finally we have the grounded specimen test with guard. And what that means is we're going to guard out the red lead at this point and bypass the ammeter and just measure through the ground connection. And this allows us to isolate the insulation from the high to ground. So taking a look, we can see we can do both of them at the same time, and then we can isolate, and this allows for not only isolation of the different insulation system, but also allows for a validation. And we'll look more into that in a later section where in the tables where it'll make a little bit more sense. Now, I'd like to discuss a few factors that affect power factor measurements. There are several of these. I'm just going to cover a couple of them. Well, there's more than a couple, but there are also more than this that I've listed, but I just want to highlight some of these to bring them to your attention. And the first one is transformer isolation. And it's important or pivotal that to isolate the insulation in order to gain reliable and accurate measurements. And this includes not only isolating the insulation system, as we saw with the different test modes, but also includes the existing buswork, and in the sense that the transformer must be isolated from existing buswork as not to cause any parallel capacitance that may influence your measurement. Next is proper grounding, and here we want a single point ground. And what this means is that the ground of the instrument is the ground of the substation is the same as the ground of your transformer. And this is critical for safe operation during the measurement. And also, if you don't have this single point grounding or proper grounding, this can lead to erroneous measurements, especially in the GST mode, where we've just covered, you include the measurement from the ground lead. So if you don't have the proper grounding, then that can cause some erroneous measurements or data. Next is proper selection of the test mode. If the improper test mode is selected, this could be misleading, as you may think that you're testing the CHL part of your insulation and you get the measurement for a CHG. So it's important that the proper test mode be selected for a certain section of the insulation, as not to confuse or mislead anyone with the wrong measurement. And also, as we kind of discussed and we'll look into further, these test modes can be used for measurement validation as well. Next is proper lead connection. And this is when testing power factor on a transformer, your winding should be appropriately and properly shorted. And what I mean by that is appropriately meaning you short all of your high side windings or bushings or terminals, and then all of your low sides separately. And then you also want to make sure that it's done properly, and the fact that you want to leave minimum slack in the conductor that you're using to short these, as not to cause any stray leakages to cause or affect your measurement. So you want to make sure that you appropriately and properly short your windings. Also, your high voltage lead should be partial discharge free and should not rest against the bushing or the tank when testing, as this could cause arc flashover or flashovers. So you want to make sure that that you have support on that high voltage lead and it's not resting against the bushing or the tank. And finally is the selection of your test voltage. The standard test voltage is 10 kV. This is what the factory uses as well. And this helps keep the test sets portable, helps with a good signal to noise ratio, and helps with the fact of trending. If you're testing at the same voltage every time, and with what the factory did, you can use that as a good baseline, and this allows for strong trending capabilities. That being said, you should never exceed the voltage rating of the windings. If your winding is rated for less than 10 kV, you should set the test voltage appropriately to that rating, so that way you don't damage or stress the windings at all or the insulation. So now that we've covered what is power factor, why to perform it, and we've covered the test modes and some factors that can affect the measurement, let's go ahead and talk about the delta, starting with the hardware overview. Here's the delta. It is a lightweight, rugged two-piece design where you can see the control unit rests on top of the high voltage unit, just down below, and they come in together at about 80 pounds and have this nice, again, stackable layout, which if you have the onboard computer, it really helps out. That way you don't have to bend over. It gives it a good height to where you can look down and use the instrument, as well as plug in all your connections as well. And it's also designed with standards in mind, safety, EMC, as well as shock and vibration standards. The Delta 4000 is capable of up to 12 kV and 300 milliamps, and is capable of power factor and dissipation factor testing, in which you not only get power factor measurements, but the Delta also measures capacitance or inductance, as well as your leakage current and your watt loss. And then finally, the Delta is capable of narrowband dielectric frequency response, individual temperature compensation or correction, and voltage dependence factor. And we're going to go into each of these individually at the end of the presentation, or in that last section. And then to the right, we have just a connection diagram. I'm not going to spend any time on that. I just kind of to show you, but we'll look into that in greater detail in some slides later. Another unique attribute for the Delta 4000 is its input power. Its input is capable of anywhere between 90 and 264 volts, and 45 and 66 hertz, and no more than 16 amps. But the big thing is as we all know, we would want to plug our instruments into mains power, but that may not always be the case in a substation. You may not have that luxury, in which case you have to test with a generator. And in that case, the Delta actually takes the AC signal, rectifies it, and inverts it into a clean AC signal in the instrument. So that way, in the case of using a portable generator, you have no loss in performance. So always a nice attribute. The Delta 4000 also comes with several included accessories, included high voltage lead, measurement leads, your ground leads, input interlocks, which we'll go into, interconnecting cables, as well as communication cables, your lead bag, and then software. And we're going to take a look at these individually as well. So starting with the high voltage cable, you can see it's kind of got a slide-in termination design. We'll kind of see kind of an illustration of that, where you just slide it into the high voltage unit and it locks in with a slide lock at this groove right here. Also at the connection terminal, we can see that this is kind of a multiple connection termination. You can connect several different terminations there, ranging from a hook for easy connection on terminations. And then you also have your clamp, and it's adjustable. So you have your elbow here, and then you also have the adjustable jaws to clamp onto bushings that may be larger, to ensure a good solid connection. You also have this smaller banana plug jack that is capable of performing tests conveniently on the bushing tests, so for your C1 and C2 tests. And then you have this nylon string, which is more to support the high voltage lead. As we mentioned before, when performing a test, we don't want the high voltage lead to rest against the tank or the bushing. So this nylon rope here can actually be used to tether this high voltage cable up and out of the way of the transformer to keep good clearances. Next, we have our measurement leads and ground leads. So 2 measurement leads are included, both 70 feet, one red and one blue. And then we have a ground lead, it's 30 feet, and we'll see it's a twist lock termination. And then you just clip this end onto the device under test ground, so your transformer ground. One thing to note is that the terminations on these were a spring-loaded kind of clamp, and recently we've redesigned that and upgraded that to a similar to the same design of the high voltage cable, where now you have the same joint here and the ability to put the sturdy clamp that we saw earlier on the high voltage cables. So a new design on the measurement leads there that should make it much more convenient for setting up the measurement leads as well. Next, we have, of course, our power cable on the right, but also, well, I don't want to say more importantly, because of course, without power, we can't run the test, but also without these, you can't run the test. Here we have 2 interlocks, one hand switch and one foot switch here. And you can use either one of these. The only condition is you must have 2 interlocks to perform a test with the Delta 4000. And we'll take a look at that in a little bit more detail. But again, you have to have 2 interlocks. They can be 2 hand switches, 2 foot switches, or one of each. Just need to make sure that you have 2 interlocks to perform the test. Next, we have our interconnection cables, and this concludes the connections from the Delta 4000 control unit to the high voltage unit. And this includes the power cable, the high voltage control, and then the interconnecting ground cable there. Now that we've gone over each one of those, I kind of want to show you what they look like in relation to the Delta 4000 itself. So here we have the side view of the Delta 4000 with the control unit on the left here and the high voltage unit on the right now. So going through, we can see this is where we plug in our mains to the unit. Here we have in our communication through Ethernet or USB, whether you want to control the unit externally or through a PC. And speaking of that, you have your control switch here that allows for either external control through a PC or the internal PC if included. You have the ground cable we're talking about, and this is the twist and lock termination that I was talking about, the connection to the Delta. And then you can see this is to the test ground, so you would connect this to the transformer. And one thing to note of this is, the Delta 4000 does monitor the ground. As we were talking about, it is a single point ground. And if the grounds are not a common ground and there is an open ground, this open light or open ground LED will illuminate until you have a single point common ground, in which case it'll turn off. And if it's on, you cannot perform a test. So that is one of the third condition to performing a test with the Delta, and we'll look at that again when we look at the software. But both interlocks must be depressed, and the open ground loop must be off, meaning that you have a closed single point ground loop system. And speaking of that, you have your interconnecting ground that goes from the control unit to your high voltage unit here. Then you have the high voltage power unit cable that goes between the control unit and the high voltage unit, and then high voltage control that goes between the high voltage unit and the control unit as well. Followed by that, you have your input. There are 2 of these. This is the red lead, and we can see the measurement lead there, where again the newer style has the other clip with the joint on it and the adjustable jaws on it. But you would have both the red and blue measurement leads that would go red there and then blue next to it. Next to that, you have your interlocks. Again, you need 2 interlocks, and here's an example of just a hand switch and the foot switch. But again, very important to notice that these are necessary to perform the power factor test. Then finally, just your mains breaker, your on-off switch. Next, I want to take a look at the high voltage unit. So here we have the control unit sitting on top again in the high voltage unit, where this is where your high voltage cable would plug in. So we have our high voltage cable, again with the termination that slides into the unit. So we can see it would simply slide in, and as soon as that groove is in there, you can pull back this, let go of this pullback lock, and it locks right into place. So easy to use, user-friendly, and ensures a good connection. Next, we have an example of our our power factor test connections. And this is an example like you would see in the user manual or data sheet, in which we can see the ground, test ground is connected to the test object, the ground of the transformer. We have our high voltage output from our high voltage unit, shown in this black arrow that goes to the high side of the transformer that has been shorted. And then the red measurement lead shown here that comes out and connects to the low side that's been shorted. So here you'd be performing measurements on the high side, either CHL or CHG or a combined test. Speaking of that, here's kind of another view of the connections themselves for the high side measurements. And kind of before we look at that, you can see I took this off of the test table from the software, that you can see all of the test modes are being utilized. You have your grounded specimen test, your grounded specimen test guard, and your ungrounded specimen test. And each of them to isolate different parts of the transformer as we talked about earlier. And also notice the test connections. They're all the same. So you connect to the high voltage cable to the high side, the measurement cable, which is your red cable in this case, to the low side, and ground to the ground. So following those connections, we connect our ground connection. So we interconnect our delta units and then connect to the test object ground. We connect our measurement lead to the low side as it said, so the red lead to the low. And then finally our high voltage measurement goes on our high side, and we're ready to perform all three of these tests at this point. Now conversely, we can do the same for the low side. We can see that the tests have changed. We have CLG plus CHL now, and then CLG and CHL, again with the same combined test modes of the ground specimen test with guard, and ungrounded specimen test. And you can see the only thing that we've changed now is we've swapped the connections of the high voltage lead and the red measurement lead. Now your high voltage lead is on the low side and your measurement lead is on your high side. Ground obviously is still going to ground. So in this situation, we'd still connect our ground to the ground of the transformer. We'd we'd swap our red lead now to the high side of the transformer. And then now we have the high voltage measurement on the low side, and we're ready to perform all of our low side measurements. All right, now that we've taken a look at the Delta 4000 hardware overview, I'd like to go ahead and take a look at the software overview. So the Delta 4000 utilizes the PowerDB software, in which in the top you would see the Megger logo, and you can have the ability to insert a logo of your choice here. And then you have your header information, which is consistent of your substation, the position, equipment location, the date, ambient temperature, and this would be ambient temperature of outside, as well as humidity and test status and so on. If we scroll down a little bit more, we'll notice that we have our nameplate data at this point, which includes the vector diagram, manufacturer data, year, and this here we can see oil temperature, and obviously we know we need year, oil temperature, and then your voltage and power rating for if we want to use the temperature correction with the tables, which we'll look on the next slide. But we can see we have the ability to fill in all of our nameplate information as well as our voltage. Once you type in your line-to-line voltage, it'll automatically calculate your line to ground. You put in your power rating and it'll calculate the current for you. You also have the ability to change your taps and modify them here. If you have a de-energized tap changer or an on-load tap changer, you can be sure to modify that here. Scrolling down a little bit more on the software, you'll see this is the power factor test table. And this should look somewhat familiar because we took little snippets of this part earlier when looking at the connections as well as the low side connections. But we can see we have our test modes labeled right here. Again, grounded specimen test with guard, and ungrounded specimen tests. We have our test voltage, and since we've already input the voltage of our primary and secondary, it's input the 10 kV because both sides are capable of testing at 10 kV. And then finally, we have our temperature correction factor, which in this case is 1 because the oil temperature was 20 degrees, but it's automatically been calculated for us based on the nameplate data. So we can see that that's already in there. Next, we have the hookup diagram at the top left here. Well, I guess it depends in the middle. And you can see this allows you to check the connections for your high side tests, your low side tests, or your oil tests. So for instance, if we wanted to look at our high side tests, we've already seen this, but you can see our measurement goes, or our high voltage is applied to high, our measurement on our low side and ground to ground. And the same way, if we pull up our low side, you just swap your high voltage to the low side measurement to your high side, and again, your ground to ground. Next, if you want to start a test, you would come over to the test number appropriate to the test you wish to start, and you would click that. And since I have multiple tests clicked here, you can do a singular test if you want to disable that. But if I click test number 1, it'll go ahead and perform all of my high side tests considering all of the connections are the same. So we move forward and we can see that sure enough, it's going to perform all 3 tests: our grounded specimen test, our grounded specimen test with guard, and our ungrounded specimen test, all with just the frequency variation suppression at 60 Hertz and 10 kV test voltage, which we already knew was input. Next, we just hit the start button down here, and then up will pop the interlock to start measurement window. And as I said before, these 3 things are necessary to perform a power factor test with the Delta 4000 as a safety feature, and that is both interlocks must be depressed and the ground loop must be closed. Once all 3 of those conditions are met, the test can be performed. I went ahead and continued in simulation mode in my case. So we continue. We're back to our measurement overview. The measurement is now in progress, you can see, and then it's going to update, a measurement in progress, and then it's going to update you as it takes the measurement, where you have your power factor measurement, your leakage current, your capacitance, and your watt loss. And this would continue for all 3 tests, and then populate the table, and then you'd go through the next set of tests. I went ahead and performed all of them. So as you can see, the table is already populated, and we can go through and we can see we have our capacitance measurements. And when we talked about validation for test modes, this is what we meant. So we can see that we have CHG plus CHL, and we have our capacitance here, about 9,500 picofarad. Then we have our CHG measurement next, which is coming in at 3,000 picofarads, and then your CHL. We can see here in row 4 that we have our CHL prime, which is our test 1 minus test 2, which is our CHG plus CHL minus the CHG, which should equal, again, your CHL. So just as we had said before, you can use these test modes as a validation to make sure that the test was performed properly, proper test connections, and so on. You can see that indeed these are less than 200 picofarads apart. If these had deviated with a greater value or that may be cause for concern, you may go back and check your test connections and investigate what could have been done. Next, you have your measured power factor, then your corrected power factor to 20 degrees C. Our correction factor was 1, so they're the same in this case. And then we have our leakage current and our watt loss. So again, not only are you getting power factor measurements, but you're getting all of these other important measurements where capacitance can give you indication about the condition of maybe your oil or maybe physical changes in the windings. And obviously both your milliamps or your leakage current and watt loss are going to be indicative of any deterioration or aging within your transformer installations. So all of this is important measurements to keep a track of and to trend. And and then finally we have the installation resistance, the rating. So if it's good or investigation or bad, and all of these are good in this case. So now that we've looked at the software for the Delta 4000, I want to go ahead and take a look at some of the advanced transformer installation diagnostics at this point. First, we'll start with the narrowband dielectric frequency response. And narrowband dielectric frequency response is essentially an extension of the power factor around the 60 Hertz measurement. So ranging from 1 Hertz to 505 Hertz. And what this causes is higher sensitivity to insulation problems and the ability to detect problems at an earlier stage. Also, if you have a power factor that seems good, but you really don't know, so it's right on the acceptance line, you really don't know what to do at that point, this can provide some more information, and it only adds approximately 3 minutes to the test. Looking at an example, here we have an example where we have this green or gray dotted line represented the 0.5 limit given by the IEEE. And then the black dotted line is the 60 Hertz line here. So we have our 60 Hertz measurement, which comes out just above 0.2 for power factor, which we can see well below the IEEE acceptance criteria, and we don't really see any concern with that. We would, we would put it right back online, no problem, not any questions asked. But if we run a narrowband dielectric frequency response measurement, we can see there's 10 measurements taken between the 500 and 1 Hertz. And as we can see, this allows for more information into the condition of the insulation system, and especially in the last decade of frequency in this 1 to 10 Hertz or 10 to 1 Hertz, as we can start to see a strong increase in the value of the power factor. So we can see that the 60 Hertz value is not concerning at all, but the 1 Hertz value is now upwards of 3% now. So it provides more information and gives you an indication of whether or not that power factor value at 60 Hertz is really giving you the full information. So it can really help you out on some measurements as to whether or not you need to investigate further. Next, we have an example of narrowband dielectric frequency response on an aging transformer. Or in this case, we had an initial measurement on a transformer where you can see the 60 Hertz measurement here and being pretty low, and even the 1 Hertz measurement at 0.47, and the trough, or the lowest point of this curve, at a low frequency. Looks like maybe it's 20 Hertz or so. And what this transformer was loaded, and measurements were taken monthly for 6 months. And we can see every month that the 1 Hertz power factor increases and the trough migrates towards higher frequencies. So this is these are both indications of deteriorating or aging insulation systems within a transformer. So it just gives you a more broad look at what's really going on in the insulation as it ages and starts to deteriorate. Also, another advantage of narrowband dielectric frequency response is the ability to do individual temperature correction. Now, initially, or I guess prior to, or sometimes still, temperature correction is using the industry conventional tables, and we already saw that actually. We saw in the example just before that just based on the temperature, the age of the transformer, and the nameplate data, the voltage and power rating, that we were able to get a power factor temperature correction before we even knew anything more about the transformer. So it was found that these tables were not inconsistent, but not very accurate at doing temperature correction. They overcompensated for some and undercompensated for others, as you may have the same transformer that's subject to different loading operation, maybe a different environment. So the tables were found not to be used. But you can see that it's still noted in the IEEE that all power factors are corrected to 20 degrees C. So what we did is, using the narrowband dielectric frequency response, came up with individual temperature correction using the Arrhenius equation here. And essentially, what's happening is we can see we have a frequency plot with frequency and dissipation factor. And we can see that the temperature, which we have 20, 40, 60, and 80 degrees C, causes a shift in the frequency on the spectrum. And we already know by performing the narrowband dielectric frequency response that we have dissipation factor measurements across a range of frequencies. So if we have the ability to do that, and temperature just causes a shift in the frequency, then we have that shift in frequency that allows us to cause a correction in the temperature. So it's just a matter of going between the frequency and kind of a temperature domain there. So, and this allows for the individual temperature correction of the specific specimen. because you've ran the narrowband dielectric frequency response on that particular transformer, creating the individual temperature correction for that transformer based on its health and condition, which allows for accurate temperature compensation or correction anywhere between 5 degrees C and 50 degrees C on the insulation test temperature. And here's just kind of an illustration of what I was talking about in the fact of overcompensating or undercompensating, where here in purple, we have the typical correction table for transformers. And indeed, at some areas, it is correct, but we can also see we have several different transformers of several different ages and several different sizes or power ratings. And we can see that for several of them, or for majority of them here, you overcompensate, and for the other, you undercompensate. So you can see that you get a lot of inaccurate temperature correction when using the tables. So another strong use for the individual temperature correction. Next is the voltage dependence factor, or the VDF. And this is essentially a power quality measurement of the leakage current. And it uses just a total harmonics distortion equation here. What essentially it does is it looks at the leakage current, and if it sees this distortion or these harmonics here, and they're great enough, it'll increase this percent VDF and flag it, saying that there's a voltage dependence here. And this could be due to moisture, it could be due to partial discharge. And then at that point, you would be able to perform an automatic tip-up test, which is essentially just the dissipation factor or power factor measurement at various voltages. So starting at 0.2, 0.4, and increasing and going up, and it allows you to relate your voltage to your power factor. And it's a diagnostic test used on nonlinear or high loss insulation, and allows again for the differentiation between moisture and PD related issues in the case of your voltage dependence factor. So now that we've looked at these advanced diagnostic features for the Delta 4000, let's look at the difference in the form. Right off the bat, we already know two different things that are interesting. One, the DFR column is here, and this percent VDF column is here now. So we have both of those are enabled, or both of those are enabled in the settings. Now what we would want to do is click the X's and turn them to check marks, and then enable our individual temperature correction instead of using the temperature correction tables. So we can simply press those buttons, and then the form will look more like this. Now we're utilizing the individual temperature correction, and we have the narrowband dielectric frequency response enabled for our measurements. After that, the test execution is pretty much the same. You would come over to the appropriate test you wish to perform, press the test number, and up would come your measurement overview window. You can see I'm doing a UST, so I'm doing the high to low insulation. And you can already right off the bat tell that this is already different. You can see many different frequencies here, showing that you're going to perform the narrowband dielectric frequency response measurement. Same as before, we hit start. We have to make sure that our interlocks are depressed and that our ground loop is closed. Once these conditions are met, we can move forward with the test. The measurement will be in progress. It'll start with your 60 Hertz measurement down bottom and give you your 60 Hertz measurement data. And then from there, it'll perform those 10 measurements between 505 and 1 Hertz. And you can see power factor, your leakage current, capacitance, and watt loss for each of those measurements as well. Then when completed, the table would look more something like this, where everything is about the same. We still have the ability to validate our test by our combined tests. We have our measured power factor, but this time our correction factor was calculated with the ITC. I did it with a simulation, so it chose 1, but in this case, the correction factor would be chosen based on that test specimen, and the correction factor, or the power factor corrected to 20 degrees C, would then show up in the power factor correction 20 degrees C column here. You still have your leakage current and watt loss measurements, but now where we didn't see anything in this column, we have our percent VDF. You can see it's flagged at 1, which would be a sign for investigation. But again, I was in the simulation mode, but if you were to see a red flag like this, typically your VDF would be much lower and would not flag at the red there, which would indicate, an automatic tip up. It's suggesting to do an automatic tip up test. Now, since we have the narrowband dielectric frequency response measurement, you may ask, where is all that data? So if we scroll down a little bit more, we would get a plot that looks like this, in which it plots that narrowband dielectric frequency response data, where we can see we have our high to ground, high to low, and low to ground insulation from our 500 hertz down to our 1 hertz measurement. And we have our 60 hertz I just highlighted here. So again, gives you a good illustration of the power factor in relation to frequency, and this 1 hertz sensitivity, or this last decade sensitivity, really gives good insight into the condition of your transformer insulation. Then finally, last thing I want to cover is to show you guys the ability of trending. So the Delta 4000 or the PowerDB Pro software, it has the ability to trend results. Here we can see that under me, I have a transformer that has data from 2005 to 2015. And what I can do is I can go into that and I can choose I can go into that form and choose the result that I want to trend and click trend data, and it'll trend it across all of these test dates. And you can get a plot that looks something like this and allows you to trend. So you have your initial, where I chose the row 3, which is your CHL measurement, and you have your power factor and your corrected power factor, both plotted on the same plot, and we can see we can trend this, and it gives you the days since the test. So again, strong ability in trending. You can see a nice, pretty flat line here. So it looks like this transformer did well over the range of testing. And again, so the PowerDB Pro allows for strong trending results, which is very beneficial when doing transformer diagnostics, as you want to see how it's progressed in the aging or deterioration. As if you saw a strong increase in one of these data points, then that would be a cause for concern or investigation at that point. And guys, to sum it up, power factor testing is a standard diagnostic technique that's used to determine the condition of high voltage insulation systems. And there are several different power factor test modes that are used to isolate different sections of the transformer insulation. And the Delta 4000 is a superior power factor test set with several exceptional safety features, accessories, and advanced diagnostic tools, which we just covered, including the narrowband dielectric frequency response, individual temperature control, and a voltage dependence factor. And finally, the Delta 4000 utilizes the PowerDB software that assists with the power factor connections, performing the test, and provides a clean report of your measurement data. And as we saw, the PowerDB Pro has the strong ability for trending data. Right, thank you very much. And are there any questions?
Yeah, thanks, Charles. We'll get into the Q&A section in just a moment, but I'm going to go over a few housekeeping points before we do. If you have any questions, please submit now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo of any Megger product. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar tomorrow, Narrowband Dielectric Frequency Response, Applications on High Voltage and EHV OIP Bushings. The presenter will be Diego Robolino. All right, let's jump into your questions. The first one I'm going to direct to Dinesh Chajer. Dinesh, how often should dissipation factor/power factor measurements be done on power transformers over 40 MVA? Is it annually, biannually, 5 years?
Good afternoon, everyone. So that's a good question. The testing frequency or how often you should test would vary based upon different utility practices. It would also vary based upon how critical that asset is. And if you look into IEEE standard, and if you look into like preventive or predictive maintenance, there is no set timeline that is given as how often you should perform. A transformer that is showing high power factor values, I might test that on an annual basis compared to a transformer that is showing really good power factor values. I may follow my routine preventive maintenance cycle as listed by different utilities, and every utility is different. So there is no straight answer to this thing. It would vary based upon the methods and practices followed by utility. But I would certainly say this thing: if you see a increase in trend of power factor values, then certainly you need to reduce your testing frequency so that you can closely monitor how the values are changing over a period of time.
Thank you, Dinesh. While I have you, I'll direct the next question towards you as well. Is dissipation factor test destructive to the equipment under test?
Again, these are some very good questions. So the dissipation factor or power factor test is not a destructive test. And the reason being is that you do not exceed the rated voltage of the winding, as Charles mentioned in the presentation. And not only that, you're only applying that voltage for a very small amount of time. When you perform, let's say, C high to low insulation, you are applying that voltage for no more than 30 seconds. So if you are putting rated voltage, if at all, to the transformer for 30 seconds, and that transformer is designed to see that rated voltage for 20-30 years, so certainly you are not stressing or like stressing the transformer. It's not a destructive test.
Thank you, Dinesh. My next question I'm going to be sending over to Daniel Carreño. Daniel, in regards to NBDFR, how many samples should be taken and at what frequencies?
Thank you, Michael. Hello, everyone. Well, there is no hard rule, if I can use the term. You typically take about 10 to 12 measurements across the narrowband, the DFR range, which is, again, as Charles mentioned, between 1 and 500 hertz. And again, even though there is no hard rule, if we look at the standard settings for PowerDB, which is the software that Delta uses, again, you have about 10, 12 measurements and frequencies that are not within, or not 60 hertz in this case. Again, you want to have several measurements, especially on the lower end of the spectrum, right, in the lower frequencies, as well on the higher end. So again, I'm not gonna mention each one of the steps, but you take about 10 measurements in that band between 1 and 500 hertz. You can go into the settings of PowerDB and change those frequencies as well.
All right, thank you, Daniel. Back over to Dinesh. Dinesh, should we perform the test with step voltage such as up to 2.5 to 5 to 7.5 to 10 kV?
So I will try to answer this question in two parts. Typically, you run into either dry type transformers or liquid filled transformers. When we talk about liquid filled transformers, your power factor value should not be voltage dependent. In other words, if you perform the test at 2.5 kV, 5 kV, 10 kV, you should expect the same results. And because of that reason, there is no value in performing a tip-up test unless you have PD activity going on inside the transformer. So that's for liquid filled transformers. And for dry type transformers, sometimes, depending upon the type of installation, it is recommended to perform a tip-up test. And tip-up test is exactly what the question is asking, where you increment, where you increase the voltage in small increments and go all the way up to the rated voltage. And that test is very common for dry type transformers, rotating machinery like generators. People do the tip-up test all the time. And there is a IEEE standard available as well, which talks about how to perform a tip-up test.
All right. Thank you, Daniel. Dinesh. Next question is going to Daniel. Daniel, what is the standard acceptable value for tan delta tests as well as power factor tests?
Good question, Mike. Thank you. And well, in general, right, if we look at IEEE documentation, the IEEE field guide for transformer testing, we'll see there are a couple factors to take into account to determine what is the limit for the power factor, right? If we are talking about new units, the general guideline is 0.5%. Although it also depends on both the voltage rating of the unit and the type of insulating liquid of the transformer in question. Right? If, again, it's a new unit, it's 0.5%. If that unit is below 230 kV, but if it's above that, then you want to have at 0.4% maximum. And if you have natural ester as the insulating liquid in that unit, then that limit raises to 1%. If we're talking about a unit that it's been in the field for some time, so it's been in service, then that limit becomes 1%. Again, this is by IEEE. I know we have a few attendees from other parts of the world, but there's a similar guideline coming from IEC and other international standards.
Thank you, Daniel. Going back to Charles. Charles, could you explain in more detail the ITC and the terms of the equations shown related to ITC?
Sure. So ITC essentially creates a relation between frequency and temperature based on your dissipation factor. And that's why it's necessary to perform your narrowband dielectric frequency response in order to provide you with the correct ITC, because you need that frequency sweep to be able to generate the relation into temperature. And the way that's done is through the Arrhenius equation. And that's the equation that was shown on the slide. And it's basically an equation that was born out of physical chemistry equation in which you relate a rate constant to an exponential factor, activation energy, the universal gas constant, and so on and so forth. But essentially, what the equation I showed is showing the way that you can relate the two temperatures, the change in temperature to a change in frequency. So that narrowband dielectric frequency response allows you to then shift the temperature and create your temperature correct, the accurate temperature correction based on your individual temperature correction. And so the again, that's based on the Arrhenius equation, which is a well-known physical chemistry equation.
Thank you, Charles. Daniel, is there a benefit to do power factor testing on dry type or resin cast transformers?
Sure. Okay, this is a good question. It's very commonly asked during this type of conversations and trainings about power factor testing. And the short answer is yes, right? Obviously, you don't have that liquid part of the insulation, but you can still perform the test following the rules for voltage to test. And again, you can trend those values over time to assess, how the insulation is evolving or is aging through the life of the transformer. Now, it's important to mention that you typically get a higher power factor in these type of units. But yes, you certainly can use these tools to trend and assess the quality of the insulation.
Thank you, Daniel. My next question is going to be for Dinesh. Dinesh, if you use the delta with a power generator, how does that affect the earthing, as the generator is not on the earth circuit and then the unit will not switch onto the high voltage? Or does this not matter with a power generator?
That's a very good question, I would say, because this question is coming from someone who has been out in the field and have run into these kind of situations. So as we know that many times we don't have access to your standard outlet power, and in those cases you would use a generator to turn to give the power to the unit. It is very important that whenever you use a generator, you make sure that generator is also tied to the same grounding point to which your test set and the test asset is going to be grounded. So again, the idea is to create a single point ground system. So if you connect your generator to the same grounded point, single point ground, which is your station ground, then there wouldn't be any potential difference between two different ground points, and you would be able to get the high voltage out of the unit. A lot of time, the generator might be on a truck, and I have seen that what people do is that they ground the truck, and that's how the generator gets the ground as well. So those are some of the things you can do to make sure that you create a single point ground system.
Thank you, Dinesh. Charles, can you get into more detail about how the equipment determines VDF in the tests and if it calculates it when we are doing this frequency sweep?
So the VDF is done at the 60 hertz, and basically what the voltage dependence factor is the same as total harmonic distortion, and widely talked about in power electronics. And what total harmonic distortion is a measurement that tells you how much distortion of your voltage or current. In this case, we monitor the current is due to the harmonics of the signal. So there's always the fundamental harmonic or the fundamental signal, and then you always have harmonics of that signal. And that's kind of where that equation where you had the summation on top over I1, where I1 was the fundamental measurement or the fundamental, and then the other is the harmonics. And if there is if there's enough distortion in your harmonics, then that's going to distort your total signal. So your THD, or your total harmonic distortion, will be high, and hence will flag a high voltage dependence factor. So that's the way that determines it, and it's just based on your 60 hertz, because you can do a voltage dependence factor even if you're not performing a narrowband dielectric frequency response. So it just monitors the harmonics of the signal, and basically just compares the weight of those harmonics to its fundamental. And if there's too many harmonics in that measurement, then that's where your voltage dependence factor will flag.
Thank you, Charles. Dinesh, if I have a negative factor measurement, what should I check in my measurement circuit?
So when we talk about negative power factor, usually you run into those typically on bushings, and the main reason why we see negative power factor is because of surface loss current. If the bushing surface has some contamination, some condensation because of high humidity, that would lead to some surface leakage current. And we have actually a paper that we wrote on this thing, and we would be happy to share that paper where we explained why the power factor values turn negative. And that is basically when the surface leakage current drives the phase angle between voltage and current greater than 90. When you run into those kind of cases, one thing that you need to remember is that anytime your power factor values improve by itself, let's say it was 0.5%, and then you test today around the same temperature and it comes out 0.3%, that's something that needs to be investigated. It's not a a good thing. Likewise, when you get your negative power factor, that is something that needs some investigation. And some of the things that you can do to avoid that or to overcome that is that you need to clean your bushings. And there are methods recommended in standard as how best to clean the bushings. Some other things involve that if you are in a high humid environment, you may want to perform the test later in the afternoon when the sun is out and there is less humid conditions. Some other things that people do is that they use the hot collar around the skirt of the bushing and use that hot collar to guard out the surface of the bushing. And when you do those things, you're basically skipping or guarding the surface leakage current outside of the measurement circuit, so that current doesn't flow into the measurement circuit. So there are a number of different ways you can do that. Some people also try inverted C1 method as well. So again, a number of methods are available for you to overcome negative power factor values. But once again, anytime you see values improving by itself or negative power factor, we should investigate, and we should not put that back in service. And the reason why I say that is that, let's say you clean the bushing and still the values are negative, that's an indication of internal surface leakage current, which you cannot avoid and which is not good for the bushings. So again, you need to investigate negative power factor values.
Thank you, Dinesh. My next question is going to be for Charles. Charles, why is the test performed at 10 kV?
So that's basically an industry standardized test voltage. And one of the main reasons is for immunity against electrostatic interference. Again, as Dinesh alluded to, we just wrote a paper on this. And there's one section that is dedicated to talking about electrostatic interference. But essentially, your power transformers operate with a high level of electrical noise and interference around them in substations. And what this can do is, based on your your test voltage, it can affect your signal to noise ratio. So a higher test voltage will increase or give you a better signal to noise ratio, which in turn gives you more accurate measurements. So you have test suppression capabilities, but again, you still need to increase that signal to noise ratio to establish accurate measurements. And 10 kV was the voltage that's kind of been standardized as far as a voltage that provides a good signal to noise ratio on power transformers. So that's kind of where that came from.
Thank you, Charles. Dinesh, do manufacturers provide data that can be used as a baseline for the transformer?
Absolutely. Whenever I guess utilities or the team that specifies the specification of a transformer, they typically put the power factor test to be performed at factory, and typically if the winding allows that, at 10 kV, and that should be used as a reference or a baseline measurement. Now, one thing to consider is that, as you know, that once the transformer is installed and in service, the insulation will deteriorate over a period of time. And it is a good thing to compare against the baseline. But what is even more important is to trend the power factor values with its own power factor values from previous years. And that would allow you to see how values are behaving and how power factor values are changing over a period of time. If you see a sudden spike or increase in the power factor values, then you need to perform more advanced method like Charles mentioned about narrowband DFR, DGA, or PD to look further into it. But certainly trending is the way to go when you talk about power factor measurements.
Thank you, Dinesh. Daniel, Can you describe a scenario that would require the additional blue measurement lead?
Sure, a good example is when you're testing a three-winding transformer, right? If you remember, and you will get a copy of the presentation, and you can look at those diagrams in PowerDB as well. When Charles was showing, right, how to connect to a two-winding transformers, you have three electrodes, right? Your high voltage windings, your low voltage windings, and ground. If you have, again, a transformer with a tertiary, then you have an extra electrode. And PowerDB will guide you with connections as well, but you will use the blue lead to connect the extra electrodes in all the three basic measurements that you have to perform. Another good example is troubleshooting. You can, when you get results that are not within the expected range, you can make use of that extra channel to measurement channel to troubleshoot issues.
All right, thank you, Daniel. My next question I'm going to be sending over to Charles. Charles, for testing a delta Y 115 kV over 13.8 kV unit, should the voltage applied to the low voltage winding be limited to 13.8 square root 3?
Yes, as you want to do the line to ground voltage. So you do want to take the square root of 3 of that as not to stress that winding and over voltage that. So the delta, your line is the same as your line to ground. So I assume that's why you asked just for the low voltage winding, so that the answer would be yes. You would want to divide that by the square root of 3, and that would be your rated voltage from line to ground, and that's what you would want to test at.
Thank you, Charles. My next question is going to be for Dinesh. Dinesh, how do you detect if a high power factor is due to an insulation problem or a high ground resistance problem?
So this one is a little bit difficult to find out, because whenever you're gonna have a high power factor value, basically it is pointing towards higher losses, and higher losses mean higher leakage current. And when you have higher leakage current, as I said, like your losses are higher, and but at the same time, sometimes based upon how you have connected the grounding system, your current could go higher because of the way your grounding system is, or your multiple ground path. Those could create problem, and it could artificially raise the power factor values, and it may seem like that you have high power factor values. So one way to check whether you have a good grounding system or not is, as I said, like try to use a single point grounding system. That would help you to make sure that there are no like grounding issues that you're running into. And when you have a high ground resistance, be it from the neutral to the ground, when you run into a high ground resistance problem, I would assume that you would run into a different problem than a high power factor value, because then the amount of current going through the ground would be limited, and that may cause different problem, but not high power factor. But again, high power factor can be caused because of grounding issues, and single pointing ground system is the way to go.
All right, thank you, Dinesh. Next question is going to be for Daniel. Daniel, how comparable are power factor test results carried out using different manufacturers' test systems?
Very comparable, or I should better put directly comparable, right? We need to remember that these type of measurements are not instrument dependent, although we have to be very conscious and aware of what are those factors that will affect my reading. And Charles touched on all of those during the presentation, right? One is temperature. So when we perform the measurement, it's very, very important that we register that temperature of the specimen, that we put it in the software. As Charles covered as well with ITC, we will get a corrected value for temperature using the proper method, right, which is using ITC. And again, when you are comparing to different units, make sure you are either comparing values of the same reference temperature, or again, making sure that the conditions were the same. The voltage is not a factor that will affect the readings. You can make measurements at different voltages using different units. If the other conditions are the same, the power factor value should be the same as well. And obviously frequency, as you can clearly see from the graphs of narrowband DFR that Charles showed, yes, you get different readings. So take into account those factors, make sure that the conditions are the same. And again, the instrument shouldn't be a factor in terms of compatibility, or that the results should be different from instrument to instrument.
All right, thank you, Daniel. And I think we have time for one last question. I'm going to send it over to Dinesh. Dinesh, our PF test came back with a range of leakage current and capacitance from unit to unit, differing from unit to unit as well. Could you explain the range and the best way to interpret leakage current and capacitance?
So when you perform power factor measurement, obviously you not only just get the power factor values, you also get the capacitance, leakage current, and Watt's loss. So when you are evaluating your results, you not only look at the power factor, you look at the other parameters as well. Typically, when you talk about capacitance, anytime there is a mechanical change in the insulation condition, if something has got compressed or shifted, it would lead to change in power. It would lead to change in the capacitance value. And typically, if the capacitance value change more than 5%, that is a indication of something needs to be further looked at. And one test that you would perform would be the SFRA test, because we are talking about mechanical changes. And the reason why a change in capacitance is something that is serious is that you have compromised the integrity of the insulation geometry. And if you look at the formula for capacitance, it's basically the area, it's directly related to the area between the plates and the distance between the plates. And that's the reason why when the capacitance changes, it's an indication of mechanical change. Now let's talk about the leakage current. So leakage current is what is used to determine the power factor. It is used in the calculation of power factor. And a lot of time when people just look at the power factor value, and the power factor value is very, very small, and it could be because the leakage current isn't flowing there, and that no flow or very little flow of leakage current could be because of number of reason. It could be instrument or the operator error. It could be wrong connections. I've seen cases where there is a electrostatic shield between the high voltage winding and low voltage winding, and because of that reason there is a very small flow of current, leakage current flow between high to low voltage winding when you perform CHL. And then you look at the capacity, you look at the power factor value, and it looks very, very good, like 0.005 or something, and you think your insulation is good, which is not the case, because you don't know that, because there is very little current flowing through. So when you're evaluating your power factor values, you not only need to look at the capacitance, but also the leakage current, watt loss, and you need to review all those 4 parameters together when reviewing the results. When you talk about the range of the capacitance and leakage current, that would vary from one asset to the other, and also what you are testing and what has been the previous values.
All right, thank you, Dinesh, and thank you all for attending. It looks like that's all the time we have for our question and answer session. We apologize if we didn't get to your question today, but we will be following up with you offline in the following weeks. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending once again. If you could please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once more, thank you all for attending. We have one more webinar tomorrow on narrowband dielectric frequency response. I would recommend you all attend. It's going to be held by Dr. Diego Robolino. But I hope you all have a great week and enjoyed our presentation here today.